In question 1, a particle of mass 8 kilogram is being pulled along the ground by a string. Okay, so I'll solve this question. This will be the last question we would answer. Okay, but let's look at okay, a person of mass 5 kilogram is in a lift. Let me make my marker ready. A person of mass 45 kilogram is in a lift. Then the lift is going vertically upward with a constant velocity. What is the reaction force of the lift on the person? This question, I think a lot of you had it correct. The solutions I had, almost each one of you had it correct. Okay, there is a lift. The lift has a support. So this is the lift. There's somebody in the lift. We are told the lift is moving vertically upwards. So the question is that it is moving vertically upward with a constant velocity. What is the reaction force of the lift? Force of the lift on the person. Okay, so once we are told that the lift moves at a constant velocity, then it means this kind of motion purely falls under dynamic equilibrium. In a dynamic equilibrium, yet the net force acting on the body must be zero, yet the body moves with a constant velocity. So once we are told the lift moves with a constant velocity, then it means that the reactional force R must balance the weight of the lift and whatever is in there. Here, we were not given the mass of the lift or the weight of the lift. We were only given the person. So mg of the person. So it means that for I, R must be equal to mg. The reactional force R will be equal to mg. Don't forget, if they gave separately the mass of the person and the mass of the lift, then the reactional force, and it moves at a constant velocity, then the reactional force will be equal to the mass of the person, connected bodies, plus the mass of the lift. So 45 times acceleration due to gravity of 10 meters per second squared would give you the reactional force, 450. All right. Then the next question. This question was a thorn in the flesh of a lot of you. Forces act on a body as shown, giving rise to the acceleration also shown. Find the vertical force R and the horizontal force P. And this is the diagram. We have this. Let me quickly clear this. So the diagram in question is like this. We have 3J Newton. Then we have another force R, the reactional force. Then we have P. We also have 17 Newton. We are given the direction of the acceleration. That is 1.5 meter per second squared. Then we have this force of 24 Newton. So forces act on the body as shown, giving rise to the acceleration as shown. Find the vertical force R and the horizontal force P. You see, in Newton's first law, okay, Newton's first law of motion says that when the body is at rest, it will continue to be at rest, and when it is in motion, it will continue to be in motion unless acted upon by an external force or a net force. Okay. Now, so if a body is at rest or is in motion, here it being at rest or it being in motion with a constant velocity means that the net force acting on it is zero. Okay, the net force is zero, acceleration is zero. Class, when it happens that the body accelerates, okay, when the body accelerates, in the same first law, the body would either be stationary or will move with a constant velocity unless it is acted on by an external force. Now, when the body is acted on by an external force, it will now accelerate. So it means that every acceleration requires an external force. The external force must not be zero. The resultant force must not be zero. The net force must not be zero, so long as there is acceleration. And this is an application of Newton's second law of motion. F, the second law of motion is that F is directly proportional to the acceleration, or acceleration is directly proportional to F. And that's how come we realize that then every force can be measured by its mass times acceleration. So this force must not be zero. F, for the body to accelerate, F should not be equal to zero. All right. The question I gave you falls under second law. There is an acceleration given by 1.5 meter per second squared. And once there is an acceleration, then it means that the body accelerates due east. Okay. It implies that bodies also accelerate to the direction of where the force is greater. So it means that then if it is moving in the direction of P and this thing, then it means the total forces here must be greater than what is here. So if I want to calculate for the net force in the direction of the acceleration, then the resultant force or the net force must be equal to what is accelerating here, then P plus 17 minus what is happening here, 24, would give me the net force. If supposing you equate 17 plus P to 24, what are you implying? Yes, class. Supposing I equated this plus to 24, what am I implying here? Or what's the meaning of such equation? Yes, Inshura. what will
The
be,
forces on both sides are equal.
and so yes, the forces are equal, and so the resultant
Uh,
force is what?
Zero.
Zero. And so if the resultant force is zero, what do we expect for acceleration? What do we expect for acceleration? Class, to the class. If the resultant force is zero, what do we expect for the acceleration?
I expect the acceleration to be zero.
Okay, so in that case, if the body is in motion, what must happen to the velocity? If in this case, if the body is in motion, what must happen to the velocity? Yes, I need a response from you. It can be anybody. So if the acceleration is zero and the net force is also zero, what must the if the body is moving, what must the velocity of the body look like?
The velocity must be constant.
The velocity must be constant. So get this right. Okay. Okay. So once it accelerates, then we need to get a resultant force. And the resultant force must be the greater one minus the lesser one, because bodies accelerate in the direction of the larger one. So this is P minus, what is 17 minus 24? That must be right. That must be 7. And so to find P, Newton is telling us that any force is given by mass times acceleration. So equate ma, m times a, to your net force, which is P minus 7. Okay. What is the mass of this? The mass is given. The mass is given as its mass is 3. Its mass is 3. So 3 times the acceleration, which is 1.5, would be equal to P minus 7. Therefore, P would be equal to 3 by 1.5 plus 7, which is, what is 3 times 1.5?
4.5.
So this is 4.5, 4.5 plus 7, which will give us 11.5 Newton. So that's the answer for P. That's the answer for P. Now, once the body only moves horizontally, it means vertically there is equilibrium. Once the body moves only horizontally and doesn't move vertically, then what it means is that there is equilibrium vertically along the vertical, but horizontally, because this is greater than this, there is no equilibrium. Mami Arba, go ask your question.
Yes. Mr. Dia, please, the 3 grams, why didn't you change it into kilograms?
Mami Arba, it is, this is, you see, look at it. This is 3J Newton. The J is just gravity. Okay. It does not mean this is gram. Once there's Newton, it means it's 3-letter J Newton. The J is for gravity. So if we are looking for its weight, then it must be 30, 3 times 10, 30 Newton. Okay. So it doesn't mean that the mass is in gram. No. The Newton tells you that the mass must be in in kilograms. So there's the mass 3 kilogram times gravity will give you 8 weight. Mami Arba, are you okay?
Yes, please. Thank
Okay,
you.
welcome. So the reactional force R will be equal to 3 J Newton, and J is 10, so 3 times 10, which is 30 Newton, to be equal to the reactional force. Okay, I hope you're okay now.
Yes, please.
Any question?
No, please.
If you have any other question, let me Chadra is here, Pierre is here, Fento is here, Gerard is here, Hendrix, Ishra, Janice, Mami Araba, and Gerard, where is Kenneth? Okay. The next question.
Sir,
Where is Kenneth?
sir, please, he's having some technical difficulties, so he's coming.
Okay. The next question. A particle of mass 8 kilograms is being pulled along a rough horizontal surface by a string parallel to the surface. If the tension in the string is 74 Newton and the coefficient of friction is 0.75, find the acceleration. Okay. Now, the moment there is a talk about acceleration, then it means Adora Otubia, the moment there is a talk about acceleration, then it implies that the what? Conclude the statement for me. If there is a talk about acceleration, then there must be a what?
An external force.
Or a resultant force, or a net force. Meaning the two or the forces acting on the body must not be the same. Because every acceleration requires a certain force. So when we find a difference, there must be a value. Please put these technicalities down. So when the question is given, I'm listening to, is there a statement of constant velocity? Hundreds and then a frontal. I'm looking for statement of constant velocity. If there is a constant or uniform velocity, then I know that the net force is what? Zero. If there is a statement of acceleration, then I know that the net force is not zero. So this is it. So this is being pulled. A particle of mass 8 kilograms is being pulled along a rough horizontal surface. So let's put something down. This is the horizontal surface. The particle is being pulled along. Along a rough horizontal by a string parallel to the surface. So this is the string. Oh, the string is here. The string is parallel to the horizontal surface. Okay. By a string parallel to the. Now the tension in the string is 74 Newton. This string has a tension of 74 Newton. If the tension in the string is 74 and the coefficient of friction, meaning there's friction at the surface, and frictional force always opposes motion. So if this tension is pulling the mass of 8 kilograms to right, then the friction would oppose it to the left. F will be here. If the coefficient of friction is this, 0. So mu is equal to 0.75. Find the acceleration of the particle. Once there's acceleration, there must be a net force. The net is the difference between two forces. So the net force or the resultant force here will be equal to once this body accelerates in this direction, the acceleration is always in the direction of the larger force. Then it means the net force will be 74 Newton minus frictional force. That will be the net force. But frictional force F is given by mu times R. Now, once the body glides horizontally on the surface, it means that the reactional force R is balanced by this mg. So R is equal to mg. Therefore, F is equal to mu times mg. Let's find F. The coefficient of friction is 0.75 times the mass is 8. Our gravity constant 10. So we put this together. We have
60.
what, 60 or 16?
Yes. So 60.
The frictional force is this. Okay. Therefore, the net force is equal to 74 minus 60, which is equal to 14. We are to find the acceleration. Every acceleration goes with a resultant force. So you are from Newton's second law, F is equal to ma. Therefore, the net force is this. 14 is equal to the mass, which is 8 by A. A therefore is equal to 14 on 8. And this is 1.75. 1.05.
75
meter per second squared. Please, if you have any questions, ask. Janice, are you okay?
Yes, please.
Janice, Fento, are you okay?
Yes, please.
Yes, please.
Joshua is gone. Okay. All right. So listen, when the question is given, you have to listen to it. Mami Araba, is that okay?
Yes, please.
Okay. The next question. The next question, which is question 1. Good. Question 1, a particle of mass 8 kilograms is being pulled along the ground by a string inclined at 30 degrees to the horizontal. So let's put the information given. Are you done writing? Okay, I think I can. Okay, I think in order not to block this, let me clear and then draw. It is always a bit easier when you are able to draw. So a particle of mass 8 kilograms is being pulled along the ground by a string. So this time, this is the ground. The particle of mass 8. This time is being pulled by a string. And the angle the string makes with the ground is 30 degrees. So the string makes an angle of 30 degrees. This is mass of 8 kg. Okay. Now, if the acceleration of the particle is 3 meters per second squared, so we are told the acceleration of the particle is 3 meters per second squared. And the resistance to the motion is 40 Newton. Find the tension in the string. So we are assuming that this body is being dragged horizontally in this direction. And so the acceleration is in this direction. Okay. Once it is being opposed by a resistance force or an opposing force, if the body is being pulled in this direction, the opposition will be in the opposite direction. It can be friction. The magnitude of this opposition is given as the resistance is given as 40. So this is 40 Newton. Okay, our question is to find the tension in the string, T. So we don't know the tension in the string. All that we know is that the body accelerates in the direction of pull by this magnitude. The resistance force is 40 Newton. The mass of the body is 8. Find the tension in the string. Okay. Key note. The body is not moving at constant velocity, but the body accelerates. Once it accelerates, then there must be a resultant force or a net force, Newton's second law. So what we have to do is that even though this is being pulled in this direction, yet the body moves horizontally. Okay, the practical application is the all cars our younger brothers and sisters use. You realize that a trolley, a string is tied to the trolley and then pulled at an angle, yet the trolley moves horizontal. So even though the force of pull acts along the string, the direction of the string, but the direction of motion is still horizontal to the direction of the ground. Okay, so once the tension with some angle theta, we need to resolve to get the component of the tension. So when you resolve, this horizontal component of the tension becomes T cos theta. The vertical component can T sine theta. Now the effective force, if the resistive force, if this resistance force is not there, assuming this is not there, then the effective force which will pull the object will be simply T cos theta. But once the body accelerates, then it accelerates in this direction, in the direction of this one. So the net force will be this one minus the resistive force. Okay, the body accelerates in this direction. A is equal to 3.0. So if you are looking for the resultant force which causes the acceleration, it is the direction of the body, okay, this component minus the resistive force. So T cos theta minus 40 must be equal to the net or the resultant force. We didn't look at this component because the body, okay, accelerates in this direction, meaning it has no relationship here. And so T cos theta, theta is 30, cos of 30 minus 40 must be equal to the net force. And every force is measured by mass times acceleration. The mass of the body is 8. So 8 times acceleration is given as 3. Therefore, T cos of 30 is equal to, that is 24 plus 40, which is equal to 64. Okay. Cos 30 is equal to root of 3.2, which is equal to 0.8661 something. Therefore, T would be equal to 64 divided by 0.8661 blah blah. Please compute and then give me the final value. What's the final answer?
73.9, which is approximately 74.
This is 74 Newton to be the tension in the spring. If you have concerns, let me know to address. Hello.
So please, my homework, when I checked it, you marked,
Yeah.
I wrote F cos 30 minus 40 all over 8 is equals to 3.
Come again. F
Cos 30
minus 40
all over 8.
All over 8.
Yes, sir. It's equals to 3. It's equals to 3. And then you marked that this one wrong.
I marked which one?
Sir, the one you just used wrong.
Are you sure?
Yes, sir.
I remember something like that, but as to why I marked it wrong, maybe I marked it in the night. So in the night, a lot of things. But you see, usually follow the steps. Okay.
Yes, sir.
Yes, 8 dividing doesn't make it wrong, but you have to put T, and then the next force must be equal to that. So follow the steps. Insura and Adwa, Akuya, any question? Any question?
No, please.
Okay. Now let's come to a very important application of Newton's first law of motion. Let's discuss applications of Newton's laws of motion. The first law, Newton's first law of motion, is also referred to as the law of inertia. What does it mean? Why is the first law known as the law of inertia? Equiadoma. Why is Newton's first law also known as the law of inertia? Equiadoma, I've called you.
Mr. Dear.
Why is the first law also known as the law of inertia? Hey, Equia, you are quiet. Okay, Inshira. Why is the first law also known as the law of
Mr. Dear.
Equia? Don't waste my time. Answer my question.
Mr. Dear, because of the reluctance.
Because of what? Okay,
Because
Inshira.
of the
Equia, let somebody else come in. Time. Why is the first law also known as the law of inertia? Inshira.
Because a body has the natural resistance to change its state of rest or the position of it.
A body. A body does what? Okay. I said it in our last meeting. Let me take it again. You see, when we talk about the first law is saying that a body would either be stationary or move with a constant velocity in a straight line unless an external force acts on it. That is Newton's first law. A body will either be stationary or move with a constant, for those who join us late, or move with a constant velocity unless an external force acts on it. So if there's no external force acting on the body would either be stationary or move with a constant velocity. When the external force comes, it changes. No. So if there's no external force, the body's state will be the same. If no external force, the body state here we are referring to state of velocity. State of velocity remains the same. So if there's no external force, the body state of velocity will remain the same. Now, if there is external force and the body has a greater mass, if the body has a larger mass or a greater mass, then the external force must be greater. External force must be greater to change the body's state of velocity. So if the body has a greater mass, then the external force acting on it to change its velocity must be greater to change its velocity. And so practically, if you are stationary, okay, if two people are stationary and they have different masses, a greater mass will be required to push the person with the greater mass. For the person with a smaller mass, just a small push. So the larger the mass, the larger will be this external force required to change the body's velocity. Is that okay? Please, is that okay?
Yes, please.
Now, when the body is moving with that velocity, and there's an external force to also change its velocity, when the moving body has a greater mass, a greater force will be required to also increase the moving body's speed. Is that okay? So the greater the mass, the greater the velocity. Sorry, the external force required. So we realize that force is directly proportional to mass. And then a measure of a body's inertia is determined by the mass. When a body has a greater mass, it will automatically have a greater inertia. Is that okay? So that is the reason why we relate the law of inertia to the first law. Now the first law is also known as the law of inertia, because if you want to change a body's velocity when either it is at rest or it is moving, the external force required to do that is directly proportional to the mass or the inertia of the body. Okay, so the force is directly proportional to the mass or the inertia. Hence, the first law is said to be the law of inertia. Please, this is an examinable area. We often ask questions, okay, about this that explain why Newton's first law of motion is also referred to as the law of inertia. And we will expect you to relate the external force required to change the body's velocity to the mass, which is its measure of inertia. Please, I hope it's okay. Mami Araba, is that okay?
Yes, please.
Adua, Otubia, Inshira, and the rest of you. I hope you are fine.
Yes, please.
Okay. I'm recording, so later if you want to put the words together well, you can pick it from the recording. Now, application of the first law is in the use of the seat belt in cars. Our bodies, everybody, a body, anything with mass has a natural inertia. It means that we naturally oppose a change in our velocity. If we are at rest, we want to continue being at rest. If we are moving, we want to continue being in motion. The moment I'm at rest and you want to change my velocity of 0, I will oppose it. Anybody with mass would oppose it. So naturally, we oppose a change in our velocity. If you don't know or you haven't experienced it, let me draw your attention to. You see, when you are in a car, in the seat, and the car starts moving, the moment the car starts to move, you will be leaning back in your seat. Though the car is moving forward, but you will be resisting the car's velocity. And you see, you were initially at rest, velocity 0. The car is moving. We expect that you move, your body moves with the car. But what happens is that the moment the car starts moving, you will be leaning back in your seat. Please, have you made that observation before?
Yes, please.
Okay. Gerard and Kenneth, have you made that observation? Janice, Joshua, and then Toronto, I'm sure you've made that observation. Whenever you are sitting in a car, when the car moves, you are in your seat. It will take some time, then you come back. You adjust, your body would oppose the change in the velocity, and then you will now be conversant with the car's velocity. Then the car seat will push you to adjust yourself to the velocity of the car. Now, when you are in it, the moment the driver applies the brake to stop, the brake would increase friction, okay? And then the moment the driver applies the brake, the driver is going back, okay? Or the car's velocity is retarded, but you will be moving forward. When the car is going, okay, retarding, you will be accelerating. You see, there's a change in the car's velocity and it is retarding, but your body will still be accelerating forward because naturally bodies oppose change in their velocity. That is why when you are in a moving car and you don't put your seatbelt, if the car is moving at a greater speed, the moment the driver applies a quick and a sudden brake, then you'll be rolling forward while the car is leaning backward. This is how naturally we oppose a change in our inertia, or we oppose our natural inertia. Any questions?
Mr. Dia.
Hello, Equia.
Please, is it true that if you have maybe an orange in a car and like it's moving with the same velocity as the car and you throw it outside the car, it will in the direction of the car, not?
When you throw it outside the car, in the direction of the car, what happens?
Will it still move in the direction of the car?
It's never true.
Before stopping.
It's never true. Don't forget it. When you take it and throw, you are not applying the same force on the orange as the force produced by the car. The engine, you see, the car engine pushes the people within and pushes the mass of the car. So there's a force which is moving all these masses. So when you take the orange and you throw, you are not applying the same force on the orange as the engine is pushing the car and all the occupants. So it is not the same force exerted on the orange. For the orange to move at the same velocity as the car. It's never true. Okay.
Okay, Mr. D.
All right. So this is the reason why if you have taken a public bus before, if you are in a public bus and then you don't hold that strength and the driver applies the brake, you are going forward. You'll be thrown forward. That is why it is not advisable to stand on top of a moving bus. Because when you stand on top of a moving bus or train and the driver suddenly applies the brake, you would accelerate forward when the car is decelerating. So you'll be thrown forward. Now, this is the reason why it is always advisable to put on your seatbelt when you are in a car. The reason is that if there's a sudden break during the course of the driving, there is the need to apply a quick brake or something, an oncoming something hits the car. The moment an oncoming vehicle hits the car, it will exert force on your car, naturally by an external force. The external force would also change the velocity, but our body naturally opposes a change in our velocity. And so while the force hits your car, okay, as a result, retarding it, you would oppose that change by moving forward. So if you don't have your seatbelt, you can be thrown out of the windscreen. But when you have your seatbelt on, whilst you are moving, it will just pull you back. This is an application of the first law of Newton's first law of motion. Are we okay?
Yes, please.
Are you writing?
Yes, sir.
Okay. Then an application of the second law. You see, the second law is about external force causing an acceleration. So any accelerating body, being it a human being accelerating a car or whatever, falls under the doorstep of the application of the second law of motion. Any accelerating body, okay, it falls under the application of the second law. Then the third law, application of the third law. Newton's third law is about action and reactional force. To every action, there is an equal and opposite reaction. And so it's always about two pairs of forces. So the first application of Newton's third law can be seen in rockets, the launching of rockets. The launching of rockets. Rockets are launched as a result of a tremendous burning of fuel within the tank. Now, when the fuel, the exhaust of the burning fuel is made to escape, the escaping gas at the nozzle can exert or escapes with some force. But because Newton is saying that forces move in pairs, whilst there's a force, there will be a reversal force on the rocket. So as the gas is made to escape, that reversal force is what pushes the rocket up. I witnessed somebody riding behind on a motor. Okay, he was a second passenger. Then another motorist, played careless. And then when he got close, he wanted to maybe punish him by just stretching his leg and then hitting the leg with the motor. Only to realize that, yes, you exert a force on the one, but because there is a reversal force on you, the person also ended up falling into a ditch. The other one fell, and theirs also fell. Because he had not done physics before, he didn't understand the concept of action and reactional force. So you cause me to fall, you also fall in the process. So another application of uh, the third law is on the recalling of a gun. Recoiling of a gun. When you shoot, when somebody fires a gun, okay, the bullet moves with a certain velocity and so has a certain momentum. There is a reversal momentum exerted on the gun. So the bullet is fired, goes out with some momentum. It also exerts a reversal momentum on the gun. So those, if you are not a very good fire of the gun, when you target and then you shoot, you can miss direct, because the moment you shoot and then the bullet moves, there's a force, a reversal force exerted on the gun. So it will also shake you. And if you are not a professional, the target can be changed. You are shooting something, but before you realize you are shooting somebody else because of that reversal force exerted on you by the bullet while it is escaping. So the recoil of a gun also falls under the application of Newton's third law of motion. Then you see this firecrackers. We are in the Christmas period. You see firecrackers being launched into space and all that. The firing of this firecrackers, or the launching of them also falls under an application, especially those ones that are put, okay, launched on the ground, and then when the matchstick is fired, there is a burning of the gunpowder. So it burns, and then whilst it burns, the escaping gas also exerts a force on whatever it's made with, and it launches into the air. So these are some of the applications of Newton's third law of motion, action and reactional force. Any question? Any question? Or any contribution to all that I've said? Hey, you are quiet too.
Sir,
Okay. Uh-huh.
sir,
Yeah.
sir, please, can we say the use of a catapult in Newton's first law?
First law. And how would
Yes,
you
sir.
how would you explain that in line with catapulting? Uh-huh.
Sir,
Let's see if it works.
okay, sir, so when you hold a catapult
Mm-hmm.
and you aim, as you aim, see the detonation is stationary. Now when
Mm-hmm.
you leave it, you see it will keep going. But even though you are not applying the force, you are not still applying the force, but it's still going.
But this one, it
That
should be under second law, because by you stretching it, you are exerting a tensional force, an external force on the mass, and it will accelerate because initially the velocity was 0. Okay, so it should fall under
yes, sir.
it must fall under the second law. Okay, a question for the house. A question for the house. A boy of mass. Let me give you a smaller one before we come to the boy. As for the boy is stubborn, so let me give you a non-stubborn boy. Are you ready? A, a particle of mass 4 kilograms is being pulled up on a smooth slope of 35 degrees to the horizontal, so hold on, because I think we haven't discussed something inclined plane. Let me give you a smaller one. A tile of mass 5 kilogram, a tile, T-I-L-E, of mass 5 kg, slides down a roof. A tile of mass 5 kg slides down a roof which is inclined at 40 degrees to the horizontal. A tile of mass 5 kg slides down a roof which is inclined at 40 degrees to the horizontal. Assuming the roof is smooth, find the acceleration of the tile. Assuming the roof is smooth, find the acceleration of the tile. I take it again. A tile of mass 5 kg slides down a roof which is inclined at 40 degrees to the horizontal. Assuming the roof is smooth, find the acceleration of the tile. Let me give you 5 minutes to think through it. Okay? Think through it, try to solve it, then we together answer it. So start work. This is about an inclined plane. Also under Newton's laws of motion.
Mr. Please. Mass.
Come again.
Please, what's the mass?
The mass of the tile. The mass
Yes,
is
please.
5 kilograms. 5 kg.
Sir,
Mm-hmm.
so I did something.
Okay. So let's
So
we'll discuss it generally. Okay.
okay, sir.
Just look at what you're trying to when we when we discuss it and you are correct, you see. So So 2 minutes more. Adwa, Insha,
Yes, please.
finish. Finish. Johnny, hey, where are they? Okay. All right. So let's see. Let's see. So a tile of mass 5 kilogram slides down a roof which is inclined at 40 degrees to the horizontal. So if this is the horizontal, the roof is inclined at an angle of 40, and one of the tiles slides down the roof. Assuming the roof is smooth, find the acceleration. So, Gerard, what did you get for the acceleration? What value did you get?
Service, I had 6.4278.
Okay, meter per second square.
Yes, sir.
Equia, what did you get?
6.43.
Okay. Equia, what did you also get?
Mr. Deputy, that is the same answer.
Equia, I will say Equia. Adwa Otubia.
6.43 meter per second.
Inshira. Her microphone problem. Janice, were you able to solve it? Mami Araba,
Yes, please.
were you able to solve it?
Yes, please.
What did you also get?
Please, I had 6.43 meter per second.
6.43, the same, almost the same value. Hendrik, did you solve it?
Please, no.
Okay. So let's see. The concept of an inclined plane is like this. On an inclined plane, this is the weight of a body mg. The reactional force is always perpendicular to the surface on which the body lies. So R is here. If this is theta, this is also theta. Now, when you resolve the weight, there is a component of the weight which is always perpendicular to the inclined plane. So this is mg cos theta. There is also a component of the weight which is parallel to the inclined plane driven by mg sine theta. And this is the reason why whenever you drop body on an inclined plane, it is always accelerating down because vertically R is balanced by mg cos theta. But horizontally, mg sine theta is unbalanced, meaning it has no balancer at the opposite end. So this is unbalanced. There's nothing which balances. So when you place an inclined plane and you put something on it, it is always accelerating downwards, down the inclined plane. Okay. Now let's apply it to, we have the mass of this is 5 kilograms. The angle of tilt is 40. So this is 40. Meaning this is also 40 degrees. Okay. Once this is 40, we can easily find the component of the weight which is parallel to the plane, to the inclined plane, given by the mg sine theta. But the question is that a tile of mass 5 kilograms slides down a roof which is inclined at 40 to the horizontal. Assuming the roof is smooth, find the acceleration of the plane. Okay. Assuming the Gerard, what's the question? Your hand is up.
Sir, please, how do you know that the angle between mg and mg cos theta is 40?
Oh, I think we have proven this. I didn't prove this with you. Okay, so this is also 40 because of this. Please, let's all pay attention to understand some of the proving. So draw another inclined plane. This is the horizontal, this is the plane. This angle of tilt is theta. A body lies on the plane in this manner. The weight of the body is always in line with gravity. So the weight is always perpendicular to the ground, horizontal. So once this is the ground, the weight of the body will always be perpendicular to it because of the direction of gravity. Now the reaction force is like a glue which sticks the two bodies together, which always presses the two bodies together. So a reaction force is always perpendicular to the surface. So this is the reactional force R, the force which presses the body to the inclined plane OA. So this is the length of the plane. Okay. Now, Gerald, look at something. You see, this is a reaction. It's always perpendicular to the ground. So this angle from the reaction to this point is supposed to be 90. This line is also an extension of the same reaction. So what do you think will be the angle from the plane to this line? Yes? Yeah. Hello? Oh, whoever asked the question is gone. Ejawadu. Hello?
Hi.
Gerard, are you there? Okay, let me continue. So the angle between this and this is 90. Plus, what would be the angle from here to this? This will also be what?
Also 90.
So this will also be 90. So O, maybe B, C, and D. Angle, the angle O, B, D. Angle O, B, D is equal to 90 degrees. The angle at B. No. What angle will be angle O? Let me shift this. What will be angle O, B, C? Now, if this is theta, the angle at O is theta, and this is 90. What will be angle OBC? Yes.
The 90 minus theta.
So that will be 90 minus theta because this is 90. This plus must give us 90. So this will be 90 minus theta. Now we are interested in angle CBD. Angle CBD. Assuming this is X. We just saw that this whole angle will be 90. So if angle OBC or X angle X plus angle OBC must be equal to angle OBD. Okay. And this must be equal to the whole of this angle. And we know this to be X. We found this to be 90 minus theta. So let's put them in. So it means that X plus 90 minus theta must be equal to angle OBD, which is 90. Please help me find X. Gerard, are you there? Gerard.
The X is theta.
So you realize that the angle X is equal to theta. Okay. That is the confirmation that if you're on an inclined plane, if the angle of tilt is theta, then the angle between the weight and then the mg cos theta will also be theta. That's the reason for which, if this is given as 90, this is also, sorry, if this is given as 40, this is also 40. Whoever asked the question is not even around. Kenneth, you have to tell me. Okay, so let's come back to our question. So we are told that it accelerates. Okay, a mass of 5 kilograms slides down a roof which is inclined at 40 degrees to the horizon. Assuming the roof is smooth, find the acceleration. assuming the roof is smooth, what it implies is that it means there's no friction working against it. There's no frictional force working against this. So there's no opposition. It means the resultant force, which is accelerating the down, only due to the always existing mg sine theta. So resultant force is equal to mg sine theta because there's no opposition at the other end. So take note that if there is an opposing force, then the resultant force will be, because it is accelerating this way, this minus what is opposing. I'll give you a question of that so you could apply. So here, the resultant force is equal to this. M, we are given 5. J is 10. Theta is 40. So sine of 40. We have to find the acceleration. Every force, whether resultant or net force, is given by M times A. So A would therefore be equal to 5 by 10 times sine of 40 divided by the mass, which is 5. So we have 5 cancelling 5. Therefore, the acceleration is given by J sine theta, which is 10 times the sine of 40. So what is sine 40? Sine 40 is equal to 0.642. Therefore, when I multiply this by 10, I have 6.423. For the acceleration, A is equal to 6.423 meter per second squared. And I think the answers you gave me were just on point. Okay. Hey, you are not happy. Okay, another question for you. Please put it down. A ring of mass is that a blue ring.
Hello, sir.
So this is, are you there?
Hello.
Hello, can you hear me? A ring of mass 4 kilograms. A ring of mass 4 kilograms slides down a straight wire. A ring of mass 4 kilograms slides down a straight wire inclined at 30 degrees to the horizontal. Inclined at 30 degrees to the horizontal.
Sir, please, can you take it again?
A ring of mass 4 kg slides down a straight wire inclined at 30 degrees to the horizontal. The coefficient of friction between the ring and the wire is 0.1. The coefficient of friction between the wire and the coefficient of friction between the ring and the wire is 0.1. Find the acceleration of the ring. Find the acceleration of the ring. Then B, if the wire is 2 meters long, and the ring starts from rest, if the wire is 2 meters long and the and the ring starts from rest, what is its speed when it reaches the end of the slide? If the wire is 2 meters long and the ring starts from rest, what is its speed when it just reaches the end of the wire? When it just reaches the end of the wire. All right, so I think 6 minutes will do for this. 6 quick minutes will do for this. So make me proud. So Panto and Hendrix is just the same application, okay? Similar to the first one we saw, but this one there's an opposing force. Just that. So just try. Good. So this is inclined at 30 to the horizontal. We are told there's a ring. It's slide down. The mass is 4. If the coefficient of mass is 4 kg, if the coefficient of friction on the surface is 0.1, mu is equal to 0.1. What is the acceleration? So once the ring slides down, then it means the opposing force is in the opposite direction. Friction will be here. Okay, so the acceleration must be equal to the difference between the forces. Downwardly, we have mg sin theta. Upwardly, we have the friction. So the resultant force Fnet will be equal to mg sin theta minus friction. Okay, and so frictional force is also F is also mu R. On an inclined plane, R is equal to mg cos theta. So we have mg sin theta minus mu mg cos theta. So we have mg out, sin theta in, minus mu cos theta within. For the Fnet, I'm just playing around formula. Okay, I need m is 4, j is 10. The angle of tilt, this is sin 30 minus 0.1 cos 30. Therefore, what happens is that, what are we looking for? Acceleration.
Yes, sir.
Hello?
Yes.
Hello?
Yes.
Oh, I'm listening. Speak.
Yes, so that means that we will divide this one by 4. Oh.
Yes, so 4 by 8, we are looking for acceleration. Okay, so A would be 4 by 10 and sin of 30 minus 0.1 times cos of 30. 4 cancels out. A is equal to sin 30 is 0.5. Multiply 0.1 by cos 30. Yes. Oh, hello. I said multiply that 0.1 by cos 30 and tell me what the value.
0.086.
So this is 0.08660. So subtract and then multiply this by 10. Subtract and multiply that by 10. Adua and Priya respond and let's move on.
4.1.
4.133.
4.133 meter per second square. So looking at what you gave me, I think the closest is the 8. None of it is closer. None of the answers given is closer. What happened? Check to see what happened in your solution. 8660 times 10. 4.134. Okay, then the velocity just before it hits. Okay, if the length of the plane, and this is by using equations of the inclined plane. S is equal to ut plus half at squared. On an inclined plane, the acceleration is equal to j sine theta. So when you substitute this, the speed, sorry. We are looking for the speed just before it hits on the ground. So we need to use v squared is equal to u squared plus 2 a is j sine theta. Okay, 2as. There's the s. Okay. Now it started from rest, so u is 0. So if u is 0, then v squared is equal to 2 times 10 times sine of 30 times the length of the plane, which is 2 meters. So we have 20 times half times 2. Therefore, v is equal to the square root of 20, which is 2 roots of 5. And what is 2 root 5?
.447.
So 4.47 meter per second will be the velocity. So as for this, one of it is closed. So this is the solution.
Sir,
Is
why are we adding the u sine theta to the j sine theta? Why are we not using the u sine theta square?
This one.
Yes, sir. Like we should have brought it rather to u sine theta square.
Which one? Which one?
So the v squared minus u squared. V squared is equals to u squared plus this one.
And you are saying we have to use what?
I'm saying that why are we not using adding the sine theta to the u squared, because at the end the velocity is being affected by the.
No, it started from rest. The initial velocity is 0. U is
okay.
0 because the motion started from rest.
Okay.
Hello.
Please, you did not give the length of the wire. You said that the wire is 2 meters round.
Mm-hmm. It's this length. The 2 meters is the length of the plane. That's the length.
Yeah, by the way you stated it, it was like the weight of the.
Remember, I said the weight of the. I said the length. If the question said if the length of the wire is 2 meters long.
I had 2 meters wide. Okay.
Okay. So I'll send you a question. Okay, a bit challenging question so that you try. Okay, I think our time is 8:55, so we'll end here. But I'll send you another challenging question on this so that you do it and then send it to me. Okay. All right, class. Okay. So let's end the class here.